Good morning, everyone. Today, we will dive into the fascinating and essential topic of performance tuning in relational databases. Efficient databases are the backbone of modern applications, from e commerce websites to large scale enterprise systems. In this session, we will explore practical techniques to optimize database performance, ensuring fast query responses, reduce costs, and improved user experiences. I'm Dr. Sumit Chauhan, Associate Professor MER Group of Institutions, will guide you through this exciting journey today. So, what is performance tuning? In simple words, it is the process of optimizing database operations to improve their efficiency while minimizing resource usage. Imagine a highway. If traffic is well managed, vehicles move smoothly. Similarly, in databases, performance tuning ensures queries are executed efficiently. But why is this important? Faster queries means happier users. No one likes waiting for a web page to load. Efficient databases also reduce the strain on resources, saving money on hardware and improve scalability. Performance tuning is a key skill for any database professional. Response time measures the duration from when a query is submitted to when the first result is returned. It is influenced by factors such as query complexity, indexing, and the database's physical storage design. For example, a poorly indexed table might require scanning millions of rows, leading to prolonged response times. Optimizing response time ensures that applications remain responsive and meet user expectations. Throughput reflects the database's ability to handle a specific number of transactions within a given time frame. A high throughput system can support multiple concurrent users and complex queries efficiently. Factors like parallel processing, efficient query design, and hardware configurations impact throughput. Enhancing throughput is crucial for transaction heavy systems like e commerce platforms. Resource utilization metric assesses how efficiently the database uses CPU, memory, disk input output, and network resources. High resource utilization without performance degradation indicates efficient operations. However, consistent resource saturation may signal the need for tuning or hardware upgrades. Balancing resource usage ensures the system remains stable under peak loads. Concurrency refers to the database's capability to handle multiple simultaneous connections or transactions. Efficient concurrency management prevents contention issues such as locking or deadlocks, which can degrade performance. Techniques like connection pooling and transaction isolation play a significant role in optimizing concurrency. Talking about the performance bottlenecks, inefficient queries often include unnecessarily joins, poorly written subqueries, or lack of appropriate filtering conditions. For example, a query retrieving all columns instead of specific ones increases data transfer and processing times. Optimizing these queries by refactoring or applying best practices can significantly improve performance. Indexes accelerate data retrieval, but their absence or misuse can lead to full table scans, especially for large datasets. For instance, searching for a customer by name in an unindexed column requires scanning every row. Proper indexing strategies like creating composite indexes for multi column condition queries alleviate this bottleneck. When multiple processes compete for limited resources such as CPU cycles or memory, performance declines. This issue is common in multi user environments where simultaneous heavy operations occur. Resource contention can be mitigated by workload distribution, query prioritization, and hardware scaling. Long running transactions that lock resources prevent other operations from proceeding, leading to blocking. Deadlocks, where two processes wait indefinitely for each other, exacerbate this issue. Implementing shorter transaction, proper indexing, and deadlock resolution mechanisms can help mitigate these problems. Complex schemas with unnecessary relationship or poorly normalized tables increase query complexity. For example, storing redundant data across tables causes inconsistencies and increases update times. A well designed schema balances normalization for data integrity and denormalization for performance. Analyzing a query execution plan provide a roadmap of how the database processes a query. By examining these plans, developers can identify insignificant operations such as full table scans or redundant joins. For example, a queries plan may reveal that an index is not being utilized. Tools like Explain or graphical interfaces in database management systems help visualize these plans for optimization. We can also rewrite queries. Rewriting queries involves restructuring them for efficiency. For instance, replacing nested subqueries with joins or aggregations can reduce execution time. Breaking down complex queries into smaller, more manageable parts ensure better readability and performance. We can also use prepared statements that improves performance by pre-compiling queries. This reduces parsing overhead for repeated executions. They also enhance security by mitigating SQL injection risks. For instance, in an application querying customer data, prepared statements prevent dynamic SQL vulnerabilities. Instead of executing multiple small queries separately, batch processing groups them into a single transaction. This reduces network overhead and improves performance. For example, inserting thousands of records using a batch query is significantly faster than individual insert statements. Retrieving all columns when only a few needed increases data transfer and processing times. By specifying the required columns, developers reduce query size and improve performance. For example, select first underscore name, last underscore name from users is more efficient than select star from users. Indexes are very important. Different indexes serve varying purposes. B tree indexes for range queries, hash indexes for exact matches, full text indexes for test search, and bitmap indexes for low cardinality columns. Each type optimizes specific operations, enhancing overall query performances. Queried columns, such as those in where or join clauses, should be indexed. Composite indexes are ideal for queries filtering on multiple columns. However, over indexes can increase maintenance overhead. Regularly analyzing and refining index usage ensure optimal performance. For example, create index IDX customer name on customers last name first name. This composite index allows quick retrieval of customer data sorted by last name and first name and ideal for search functionalities. Normalization organizes data to reduce redundancy and ensure consistency. However, excessive normalization can degrade read performance. Denormalization adds some redundancy for faster reads. Striking a balance based on application requirements is essential. Dividing a large table into smaller, more manageable partition improves query performance. For example, Partitioning a sales table by year allows queries targeting specific years to scan fewer rows, reduces execution time. Materialized views store pre-computed query results, significantly improve response time for complex aggregations. For instance, a materialized view summarizing monthly sales can be queried directly instead of recalculating the totals each time. Here we have an example. Create materialized view MV sales summary as select product ID, sum sales amount from sales group by product ID. Resource management is crucial. Allocating sufficient memory for buffer pools, caches, and temporary storage minimizes disk I/O operations. For example, increasing buffer pool size in MySQL allows more data to be cached in memory, improving query speed. Techniques like connection pooling manage simultaneous user connections efficiently. Pooling reduces the overhead of establishing connections repeatedly. Configuring maximum connection limits ensures stability under heavy loads. SSDs provide faster read-write speeds compared to traditional HDDs. Distributing data across multiple disks using RAID configurations enhances performance by parallelizing I/O operations. We need to minimize locking. Using row level locks instead of table level locks prevents unnecessary contention. For example, in an e-commerce application, row level locks ensure that updating a single order does not block access to the entire orders table. Isolation levels determine how transaction integrity is maintained. Choosing read committed prevents dirty reads, while serializable ensure full isolation but may reduce concurrency. The choice depends on application requirements. Consistently ordering transaction and setting times out for locked resources help prevent deadlocks. For instance, ensuring that all transactions acquire locks in same sequence reduces the likelihood of deadlocks. Tools like MySQL Workbench and SQL Server Profiler provides real-time insights into query performance, resource usage, and system health. These tools identify slow queries and suggest optimization opportunities. Periodic updates of database statistics ensure the query optimizer has accurate data for plan generation. Rebuilding fragmented indexes and archiving unused data keep the database performant and manageable. We'll discuss a case study. A retail application sales report generation slowed due to inefficient queries and lack of indexes. This impacted the ability of management to make timely decisions. Now, rewriting the query removed redundant joins and creating a composite index on product ID and sales date accelerated filtering. Introducing a materialized view pre-computed monthly totals significantly reducing query complexity. The final result improves the response time from 15 seconds to 2 seconds, enhancing the overall user experience and decision making speed. The best practices to follow: regularly analyze database operations to identify trends. For instance, understanding peak usage times helps allocate resources efficiently and effectively. Incorporating indexing and efficient schema design during development avoids costly retroactive optimizations. Automating performance alerts ensures timely detection of anomalies. Script or third party tools can notify administrators of high resource usage or slow queries. Regular audits adapt the database to evolving workloads. For instance, adding new indexes or partitioning tables based on recent query patterns ensure sustained performance. Lastly, to summarize, performance tuning is a continuous and iterative process. It balances resource efficiency with business needs. Start by analyzing your database's current workload, then apply the techniques we have discussed. Remember, even small changes can have a big impact on performance. Thank you for your attention.